Most people learn about solids, liquids, and gases, and if the term plasma comes up at all, it's usually, oh yeah, the stuff in neon signs. But here's the thing, plasma isn't rare, it's everywhere. You can find plasma in stars, lightning, fusion labs, and even the space between galaxies. This fourth state of matter makes up 99% of the visible universe. And yet, as common as it behaves in ways people have never even heard of or understand. It can twist, it can pulse, it can organize itself into patterns that sometimes make it seem alive. So today we're walking through 7 key terms that unlock how plasma really works. But before we get into the terms, let's get real clear on what plasma actually is. So what you're seeing here is a side-by-side comparison. On the left is a neutral gas. That means the atoms still have their electrons bound. Then on the right, energy has stripped those electrons away. This leaves behind a charged, dynamic soup of ions that are positive and electrons that are negatively charged. That transformation is what turns an ordinary gas into plasma. This can be triggered by heat, radiation, or strong electric fields. Now that you know what plasma is, let's talk about what all those charged particles start doing, because they don't sit there, they move. And when they do, when charge goes from positive to negative, it creates an electric current. Now, anywhere we have an electric current, we will get a magnetic field that forms around it. It essentially forms a circle around the electric current. We'll see as we go through more slides how this plays a major role. Okay, now with a good foundation, let's get to our first term, quasi-neutrality. This is going to talk about how plasma stays balanced, sort of. Now on the slide on the right, you're seeing that balance in action. Typically, we have a chaotic mix of charged particles, but overall, they add up to something close to neutral. That's where we get that term, quasi-neutrality. Now, it's not perfectly balanced, but it is neutral enough to hold plasma together. Local imbalances can happen, especially near boundaries or in active regions. But across the bulk of plasma, the charges nearly cancel out. This is what allows plasma to move, stretch, and self-organize without flying apart. Now let's talk about the invisible shield that makes quasi-neutrality possible. If quasi-neutrality explains how plasma stays balanced overall, then the Debye length explains how that balance holds together up close. Zoom in far enough, and you'll see that every charged particle is surrounded by a subtle field of influence, a bubble of space where other particles still respond to its electric pull. Now this slide shows a positively charged ion in the center, with a shell of free electrons clustering nearby to neutralize its field. That boundary, the distance where the charge's influence fades, is called the Debye length. Within that range, opposite charges get pulled in, like charged ones get pushed away. This balance only works up to a certain distance. Beyond that, the plasma acts like the charge was never there. The result is a kind of automatic shield around every charged particle. That's how plasma appears neutral from afar, even though it's full of electrical activity up close. And this tiny length matters. It sets the scale for how plasma responds to outside forces, how fast waves travel, and how sharply it can form boundaries. But when that local balance breaks down, when charges are separated by distances larger than the Debye length, something stranger begins to happen. Now let's talk about the third term, plasma's double layer. When plasma builds a boundary out of pure charge. This slide shows it clearly, a region where 2 layers of opposite charges form, one mostly positive and one mostly negative. They are separated by a sharp voltage drop. This is what we mean when we refer to a double layer, a self-generated electrical barrier built entirely from the motion of charged particles. It forms within the plasma, not at a boundary, which we'll see an example of that later, but between regions with different flows, energies, or densities within the plasma. You can think of this acting like a natural capacitor or an internal membrane. It's essentially a structure that organizes the chaos and creates powerful electric fields within. These layers don't just sit there. They can trap particles, accelerate them, even emit light. And you'll find double layers in auroras, in solar wind, and in high voltage plasma arcs. Some researchers believe that they're also behind the mysterious formation of plasma structures, like glowing orbs, filaments, or brief contained pulses of energy. They're not just strange, they're one of the clearest signs that plasma can create order out of chaos. Now let's get into term 4, the pinch effect. This is when plasma collapses inward under its own current. You'll see that when charged particles begin to flow, they generate that magnetic field we talked about earlier. It wraps around the current itself, and as an effect, it starts to compress the very flow that created it. You can see this process here. As the current flows through the center, magnetic loops form around it and essentially squeeze the plasma inward like a tightening coil. That's the pinch effect. The more current you have, the stronger the inward magnetic pressure becomes. Plasma collapses then into a narrow, focused filament, sometimes bright, sometimes explosive. You'll see this in fusion labs, in solar flares, and in the enormous jets that shoot from stars and galaxies. But it's not just a collapse. The pinch effect can unleash bursts of energy, trigger sudden shape shifting, or briefly stabilize the plasma just long enough for something else to happen. It's one reason that plasma so often looks like it's drawing lines through space. Look at us on to term 5 already. Now let's talk about what a plasma sheath is. This is talking about the invisible interface that occurs when plasma meets pretty much anything else. In this image here, the fast-moving electrons hit the surface first. Electrons are faster moving because they are lighter than positive ions. This leaves behind a region of positive charge just beyond it. That separation builds an electric field, pointing inward toward the material. This is the term sheath, a self-generated field layer that controls the flow of energy and particles at the boundary. It determines what escapes, what reflects, and how plasma can interact with the world around it. Inside that narrow interface, particles oscillate, fields rise and collapse, and waves ripple into the surrounding plasma. The sheath isn't just a surface effect. It's an active zone of regulation where plasma decides what comes in, what stays out, and how energy and signals move across the edge. Now let's talk about plasma frequency, the natural rhythm of electron motion. Even when plasma looks calm, it's vibrating. Free electrons are constantly being pulled and pushed by electric fields, and instead of just drifting, they oscillate. That back and forth motion happens at specific rates, and that rate depends on how densely packed the electrons are. This is what scientists call the plasma frequency. Think of it as a natural heartbeat, so to speak, of the charged particles inside. Now let's take a look at this slide to get a better idea of what the plasma frequency is. Here you can see if an incoming wave has a frequency below the plasma frequency, it gets reflected. But if the wave's frequency is higher, it passes through. So essentially, plasma can act like a wall, a window, but either way, it's a filter, all depending on the rhythm of the wave that hits it. This is why plasma is used in communications, shielding, and why signals behave so differently in space. This hidden plasma frequency decides what waves get stored, what bounces back, and what gets transmitted through. Congratulations, you made it to term 7. Before we get into it, if you've enjoyed this video, be sure to subscribe, hit the like button, share it with another curious mind, and let's learn about MHD or magnetohydrodynamics. This is the framework that explains how plasma flows, twists, and holds itself together. Essentially, MHD treats plasma like a special kind of fluid, one made of charged particles, constantly in motion and constantly interacting with electric and magnetic fields. In this diagram, you're seeing that relationship in action. Plasma carries electric currents, and those currents generate magnetic fields. But those fields don't just sit still, they push back, guiding the plasma, bending its shape, and shaping its motion. It creates a dynamic feedback loop. The plasma creates the field reshapes the plasma, and the cycle continues. This effect might sound a lot like the pinch effect, and they are related, but here is the difference. The pinch effect is like a sudden storm, narrow, intense, and focused. Magnetohydrodynamics, or MHD, is the full weather system. It describes all the ways plasma and magnetic fields interact, not just collapses, but also the waves, loops, flows, and instabilities. A great example is those huge arcs of glowing plasma on the sun, solar prominences. They are held in place by magnetic fields shaped by the plasma itself. Without that feedback, structures like that would quickly fall apart. To wrap up, let's go over the terms one last time that reveal how this strange state of matter works. We started with quasineutrality, the principle that keeps plasma mostly balanced, even when it's full of positive and negative charges. That balance holds thanks to the Debye length, a tiny shielding distance that sets the scale for plasma behavior. Double layers show us how charge separation can form boundaries, accelerate particles, and even emit light. The pinch effect revealed how plasma collapses inward under its own magnetic fields, forming narrow, focused filaments. Then at any surface, we found the sheath, a sharp, self-organized interface that controls what comes in and what stays out. Remember that even in stillness, plasma has a beat. It's plasma frequency, which decides what waves get reflected and what passes through. And finally, magnetohydrodynamics brings it full circle, a framework that explains how plasma flows, generates fields, and reshapes itself again and again. I hope this video helped you understand a few terms about plasma so you can truly appreciate how amazing it is. I know it's often called the fourth state of matter, but if you ask me, it's the first. Overall, if any of these ideas spark something for you, or if there's a term you'd like to see explored more in a different video, feel free to let me know in the comments. And if you know someone who's curious about the universe, share this video with them. It's a great place to start. If you want to keep exploring, I've got more videos linked in the description. Hopefully by then I'll have a playlist about Plasma Physics 101 or some name like that. It explores a lot of these terms in more detail. I think after this video, you're ready. Thank you so much for your time and take care.